Welcome everyone to the Greener Hub webinar series. My name is Evelyn Zuniga, and I am one of the communications officers for the Greener Hub project. If you have been here before, you know that the Greener Hub project officially started in September 2022 as a coordination and support action of the European Commission under the Horizon Europe program, and it currently represents 15 ERANETs, co-funds, and self-sustained initiatives in the field of agri-food and biotechnology. We started these breakfast clubs last year in October, and we have had very successful series. The first one was in circularity in agriculture. The second was in biotechnology to advance sustainable solutions for bioeconomy. And the last one was sustainable food systems. So if you're interested in any of these, of the recordings of this series, everything is now uploaded in YouTube. And now for these 3 months, we are focusing on the topic of precision agriculture technologies for a sustainable future. And we are going to have topic talks related to transparency across the value chain for different products, application of artificial intelligence in farming, robotics in farming, among many others. Just a few housekeeping announcements. Feel free to type your question in the Q&A section and the chat section that I have enabled for everyone. I'm going to try to address as many questions as possible with the time that we have, that is 1 hour. So if at the end of the session you have a question for either of the speaker, please address the speaker in your question. Today we have two panelists, Professor Giulio Reina and Dr. Claudio Carnevale. And we're going to open our session today with Professor Reina. Professor Reina is full professor at the Department of Mechanics, Mathematics, and Management at the Politecnico di Bari in Italy. Dr. Reina's research spans vehicle dynamics, planetary exploration robotics, and agricultural automation. His work focuses on mobility in rough terrains, advanced perception systems, and the development of hardware and software solutions that enhance the driving automation in ground vehicles. He has a strong focus on planetary rovers and precision agricultural robotics. Dr. Reina actively participates and coordinates collaborative international research projects, contributing to the development of cutting-edge mobile robotics and vehicle technology across different domains. Today, the title of his talk is Giving Smell Sense to Agricultural Robotics, which is part of the STAR project, which was funded under the ICT Agri-Food Initiative. Professor Reina, thank you very much for accepting our invitation to present your research today. And I'm just going to stop sharing my screen and you can start sharing your presentation. Thanks so much.
So, thank you, Evelyn, for your kind introduction. Let me start my presentation. Yeah, it should be working now.
Yes.
Let me thank also the audience and welcome you all this morning for my webinar, where I'm going to present the latest results within the STAR project. The STAR is the acronym for Giving Smell Sense to Agricultural Robotics. And let me start by briefly introducing myself. As you mentioned earlier, I'm with Polytechnic University of Bari, or Politecnico di Bari in Italian. Just a few geographical facts. If you see Italy as a long boot, we are at the end of this boot, so we are in the heel of the Italian boot. We are located in Bari, that is the main city of the Apulia region, that is getting very popular these days for touristic reasons. I lead the Robotic Mobility Lab. What we do is field and service robotics, not only for agriculture, but also for planetary exploration and industrial automation in general. Here on the left, you have the front page of our web page. This gives me the opportunity to say that we have many openings for postdocs and postgraduate students. So if you see your future in robotics, in agricultural robotics, feel free to get in touch and let me know. Back to the STAR project, we are coordinating the research activities along with the other research partner that is Fraunhofer Institute for Intelligent Analysis and Information Systems, Germany, while the industrial partner is covered by Todos Technologies, that is a startup, innovative startup located in Israel. STAR will cover a period of 3 years for 2023 to 26 with an overall budget of about 700,000 euros. Let's have a look at the main objectives of this STAR project that, by the way, was funded within the 22 ICT Agri-ERA net calls. So the objectives are to single out healthy fruits or plants in order to start, for example, to start harvesting in a selectively way, or apply remedy without wasting resources or contaminating the environment. In order to do that, we want to combine standard sensing technologies with novel sensing methods like the use of gas sensors in order to create accurate maps that can facilitate operation on a very narrow scale with very small environmental footprint. We want also to involve artificial intelligence as much as possible for data processing and decision support. How do we want to achieve these goals? Well, everything revolves around the idea of using a farmer robot that is at the center of this slide, our polybot robot, as we are going to see soon, that will be that is equipped with a very rich sensor suite, including conventional standard sensors like RGBD cameras or GPS, with novel sensors like sensor to measure the CO2 concentration around the plant, or in general the use of sensor for VOCs detection, so volatile organic compounds detection. You have to know that our background at the Robotic Mobility Lab is in mechanical engineering. I myself am a mechanical engineer, so I love to start by giving you some brief description about the farmer robot that we are using, we are deploying for the STAR project, whose technical details are briefly here introduced. The name of this robot is Polybot, that is the acronym for Polytechnic University of Bari robot. The nominal speed is 1 meter per second. The maximum speed is 2 meters per second. That ensures a survey performance of about 40 minutes to inspect, to monitor an hectare of crop. The payload is 50 kilos, and the main design features are the adoption of trucks that reduce soil compaction, high mobility on uneven terrain, so both highly deformable terrain and highly irregular terrain, and body isolation from vibrations. These key design features are achieved by adopting a passive articulated suspension system that is shown in this slide for the left side. While standard robots, agricultural robots using tracks are characterized by using fixed road wheels that cannot move with respect to the chassis of the robot, in our solution, the road wheels can move up and down with respect to the others, and this provides the robot remarkable mobility and adaptation ability over irregular terrain, and also allow to distribute more uniformly the weight over the two tracks. One key advantage of using this kind of architecture is that the ground pressure is as low as 7 kilopascal when the robot is fully loaded. So we are talking about 140 kilos. That is way below the threshold range between 40 and 60 kilopascal that marks the onset of soil compaction. So this is very important so that we have no impact on the agronomic and hydrogeologic properties of the traverse terrain. The passive suspension system ensures also body isolation from induced by terrain irregularities, and the RMS of the vertical and pitch accelerations have been reduced by almost 50%. That is also a remarkable result. And this is very beneficial for the sensors that are mounted on the aluminium frame that you see mounted on top of the robot. I just wanted to show you also the robot, the polybot in action along the row vineyard. Here you can see the different parts of the suspension system that work together to provide the robot with high adaptation to the terrain topography. Okay. Let me skip this one. So maybe if you have a question, I can come back later. While let me show you a dissemination video that we created in order to show the current status of our technologies for robotics in agriculture. I will mute myself during the broadcasting of the video so you can enjoy the soundtrack as well. Hopefully the audio will work. Evelyn, can you confirm that you can hear the music as well? No?
No, there's no music because there is a way
Okay.
when you share on Zoom, if you click like share sound, then it will share the sound. But it's okay, we can see everything.
Anyway, so maybe I can comment on it if you don't have the audio. So here the idea is that while the farmer sits comfortably home or working from the office, the farmer robot can be sent out to perform automatic environment monitoring on his behalf. So the farmer can set the desired area to be inspected. Upon receiving the intended mission plan, the robot starts its mission by, again, autonomously surveying the area of interest without any human supervision. During inspection, if I can, during inspection, images taken from the environment can be processed in order to get meaningful information in terms of vegetation indices. In this case, for example, the robot is measuring the GLVI index, the NDVI index, and the canopy height, so we can get also morphological information from the crop, in order to provide the farmer with important information that can be used to understand the status of the crop. So what is now the ambition that we have with STAR? So the current ambition is to add a new layer of information. Specifically, we want to provide the robot with the smell sense, with the olfactory capability, in order to measure the grape respiration rate that can be correlated with the maturity level of the grape itself. We can refer to the graph on the right that shows the relationship between the grape respiration rate in terms of CO2 and O2 with respect to the maturity level of the grape. So at the beginning, at the start, so along the x-axis, we have the day before harvesting. So at the end of this x-axis, we have the harvesting time that is marked in this case as 100. So at 100, we have the harvesting of the grape. So as you can see, the grape respiration rate in terms of CO2 and O2 drops as the maturity level of the grape increases. So we want to demonstrate this relationship using the GMOS sensor provided by the partner Todos that was mounted on board our farmer robot. So the sensor is shown on the left. We started as usual in controlled laboratory environment using an airtight box. Then we created our chamber, respiration chamber, that can be mounted directly on board our farmer robot. We call this respiration chamber the tube. Some sample observation measurement taken from the field using our system. Here at the beginning, our tube, our respiration chamber was empty. As soon as we insert a grape bunch inside our tube, the respiration rate increases with what it seems a linear trend. So then the raw data are processed using a change detection algorithm that finds when the concentration of CO2 changes significantly in our tube, but then we apply a linear fit. In the end, eventually, we are able to measure a normalized respiration rate that for this specific measurement was about 0.42 micromole per gram per hour. So this is the parameter we decided to use in order to check whether the grape is ready to be harvested. The results obtained in our first preliminary campaign in 2024, so those are very recent results, are collected in this final graph, where we are plotting the CO2 production rate, respiration rate, as a function of the day of measurement. We tested 5 different grape varieties. So we have the blue line shows the Malvasia Nera, the red line, the Negro Amaro, the yellow line, the Pampanuto. With magenta, we have the Primitivo. Finally, in green, we have the Verdeca. So we have the chance to test 5 different varieties. 3 days of experiments, early July, end of July, and the day of harvesting of the grape was beginning of September. The markers that you see here are experimental points, and what is apparent from, as can be seen and apparent from this graph, and once again, that the respiration rate in terms of CO2 is significantly lower at the harvesting time with respect to a couple of months before. So we believe that this parameter can be really helpful for a farmer in order to get a great, knowledge and inside knowledge about the maturity level status of this grape. Let me close my presentation just by also looking at the current limitation of the system. So what we have seen is that the respiration rate is highly dependent on environmental conditions and depends on the time of the measurement. The respiration chamber needs to be airtight. And so those are the two aspects we are going to work during the winter in order to be ready for the next growing season, to be ready to deploy a complete experimental campaign. Okay, thanks again for your kind attention, and let me also thank my research team that made this research possible without also enjoying the journey. It is also very important. Let's keep in touch. Again, we have many openings, so if you have interest towards agricultural robotics, let me know. I don't know if I was a bit late. Probably yes. Sorry.
No, you were right on time.
Okay.
Perfect.
Okay.
Now,
Yeah. Any questions? I'm
yeah,
open to
yeah.
questions.
So I
Or
just
even
want,
later, you can get in touch again. And here you have my email, or you can check out our webpage. And so if there are questions.
okay. So yeah, so while people type away, they can type their questions in the Q&A section and then the chat section. I have some questions. So you mentioned that the weight of the robot, it is like it has its weight, but then you mentioned that the permissible uh, pressure for the ground, it was between 40 to 70 kilopascal. Is this like a guideline for this type of
Yes,
robotic?
yes.
Ah, okay.
Actually, this is very important. Let me go back. And so, so there is like a maximum ground pressure that you don't have to exceed in order to avoid any agronomic damage due to soil compaction. So, okay, so this is a very important aspect that you have to take into account when you work or when you design an agricultural vehicle in general, not to exceed this permissible ground pressure or maximum ground pressure. So you have to be below this threshold in order to be sure that you are not going to produce any agronomic damage. So
Okay. Yeah, that makes sense. But I didn't know there were actually kind of numbers that you need to follow because there are like guidelines for this. I didn't know. I just have a question about you said that the person that is going to use the robot, they can kind of map the place where the robot is going to move. So at the moment, what is the autonomy of the robot like in time, like in hours or minutes?
no, the term is huge, I should say, since you have to know that the power consumption of this robot is very low. So the power is about 100 watt. It means that less than a bulb, an electric bulb. And so the autonomy is, we have worked continuously for 6 hours. And then the battery dropped a little bit. So let's say 6 hours of continuous working. Obviously, another positive aspect of this kind of vehicles is that you can easily remove the depleted battery and replace it with a new one, and you can keep on working. So this is
Mm,
also a positive aspect.
okay, yes. So there is a question here. It says that if you think that how would using a drone work in terms of like monitoring
Okay.
the vineyards, that if it will be better or worse, or somebody asking, what do you think?
Okay, obviously, using a drone, you can get more you can get a faster assessment of the crop from the top. And while in contrast, well, our idea is to have a more plant-by-plant approach with a very small and narrow footprints. This means that we want to be able to look at the single plant also from a lateral perspective view, while with the drone you have a top view, and even though there are sensors that can provide a high resolution, so it is also true that with the drone you can also go down to a very small footprint, so analyze the single plant. However, with our solution, we believe that you have a better assessment for the single plant with a different perspective. So actually, we are not proposing our system as in replacement of a drone. We imagine a more a collaborative behavior where a drone can soon make an assessment of a large area, detect some spot areas of interest, so detect that there is a problem in a specific point of area of the crop, and then we can send our farmer robot to inspect this specific area in more detail, looking at the plant of that area, in order to provide the farmer again with some meaningful information.
Okay, all right. We have another question here. They're asking, can these robots be used to determine soil properties and, more importantly, detect foreign objects in the soil during harvesting periods such as wood and plastic?
About the terrain properties, yes, we have done a lot of research in this respect. So in this presentation, I tried also to add the bottom of each slide a paper related with the research we did. So you can find our papers about terrain estimation. And again, this is a huge topic that we have investigated during the years. And we have developed different methods. So the standard methods use basically exteroceptive sensors like cameras in order to get color and geometrical information about the terrain in front of the robot. However, exteroceptive sensing cannot catch the mechanical properties of the terrain. So in this respect, we use trucks or wheels in other robots as a tactile sensor in order to scoop up, to get information from the traverse terrain. So measuring, for example, the forces that the trucks of the wheel exchange with the terrain, and the vibrations, the corresponding vibrations. We have built neural networks, in order to provide the type of terrain the robot was working on. So in order to be able to understand, to provide the robot with the knowledge about the terrain, if was a firm terrain rather than a very deformable terrain. So being able to distinguish between asphalt, agricultural terrain, gravel, and so on. So the answer is yes, we are. This is again a huge topic of our research. So being able to understand the type of terrain the robot is traversing in terms of irregularity and deformability, and also in order to know what is the power consumption of the robot on that terrain, in order to understand if the robot can get in trouble traveling over a highly irregular terrain or a highly deformable terrain. So we want to also develop hazard indicators in order to inform the robot that the terrain is somehow dangerous and maybe change path. Um,
Okay. Okay.
okay.
We have two questions actually about pests. So it says, can the smell sensing robots contribute to the early detection of plant diseases or pest infestations?
We haven't worked in this direction yet. We have focused on the detection of the maturity level.
Okay.
Um, so let me think. Well, we haven't looked into this aspect, but I'm sure that you can also get information also when a specific bacteria or
Mm,
mold is present, is affecting the grape.
yeah, that makes sense.
But this is not, again, is a bit of out of the scope of STAR, not
Mm,
to be the topic for sure of the next
yeah,
project.
for a
We
whole new project, definitely.
Yes.
Yes. And I'm gonna take this last question. It says, so you're mainly dealing with the robot as a sensor carrier here. Will the robot also carry and use actuators for crop treatments, etc., and even be developed for harvesting at a future stage?
Okay. Actually, we also have a sprayer, so we can mount a sprayer on the robot, so we can do also treatment using liquid fertilizer. The harvesting is also something that we have in mind, but this is again a third possible new project. But definitely, this is something that we have been thinking of for many years, and hopefully we will do in future. So adding a robotic arm with a dedicated end effector in order to gather, harvest the grape when the time has come.
Mhm. All right. Professor Reina, thank you very much for showing us your presentation. It is very, very interesting to see how robotics it's applied in agriculture and like successfully as in your case. Like I can see that this project is gonna go way like you're gonna have way more results and then more ways to the options to open up even more and get more projects uh, from this one. Yes, thank you very much for your
My pleasure. Thank
presentation
you very
and
much.
for being with us today. And now we're going to move to our next presenter, who is Dr. Claudio Carnevale. Um, Dr. Carnevale, as I said before, is Associate Professor at the Department of Mechanical and Industrial Engineering at the University of Brescia in Italy. Dr. Carnevale is an expert in air quality management and environmental sustainability with a focus on developing advanced models for pollution control. His research centers on using nonlinear data-driven systems to monitor environmental impacts and optimize decision-making for emission reductions. Dr. Carnevale has led projects creating forecasting tools and solutions to improve air quality and has participated in numerous international initiatives that influence policies for cleaner air and better public outcomes. Today, the title of his talk is Artificial Intelligence Application for Farming, which is part of the App for Farm, which is the App for Farm project funded by the ICT Agri-Food Initiative. Dr. Carnevale, thank you very much for joining us today. We're very fortunate to have you with us today. And I'm just going to stop sharing my screen and you can start sharing your presentation. Thank you so much.
Thank you, Dr. Zuniga. I'm trying to share my screen and my presentation. Is it okay?
Yes, it's perfect.
Oh, thank you very much. So thank you to be here to hear me talking about artificial intelligence application for farming. As Dr. Zuniga already told you, this is the part of the App for Farm project. This is founded on the Eranet co-founder ICT Agri-Food Co. The project has been performed with the help of a strong partnership that includes University of Florence, the National Italian Council Munster Technological University in Ireland, and GFZ in Germany. Let me start with something that probably all of you knows, but I think it's quite interesting to start with it. That is the relationship between climate change, agriculture, and how the smart farming enter in this context. So the relationship between climate change and agriculture is quite peculiar, because it is obvious that agriculture is one of the field that is most affected by climate change. Moreover, it is also one of the most important sources of some pollutant like ammonia, nitrous oxide, methane, that contribute to the accumulation of greenhouse gases in atmosphere. Greenhouse gases are the main driver for the climate change, and the one or some of the effects of the climate change are mainly related to the weather, like temperature anomalies, extreme rain period, water scarcity, and droughts, and this obviously affect agriculture. So the main thing is how to drop in such a way this circle, this vicious circle. So one possibility is making agriculture more robust in order to be able to take into account the effect on the weather of the climate change, so different climatic condition, and on the other hand, so trying to compensate the impact of this role. The other possibility, or this arrow, sorry, the other possibility is to work on this arrow. And this means, for example, making some agriculture activities that leads to lower pollutant in atmosphere. How smart farming enter in this context? Let me say, I see smart farming as strongly connected by efficiency. Efficiency in the sense that in principle we do something that smart farming didn't allow you to do something that is not possible with the traditional technologies, but allow you to do it, let me say, better, in a more efficient way. And I think the main keyword that probably already are put on the table by the previous presentation about smart farming was starting from a close monitoring, a strong monitoring, giving information to take decision in order to have great efficiency in your field. And this, when we talk about efficiency, the question that we have are not so complicated in a semantic point of view. The answer are complicated, but the question are more or less three: when, where, and what. These are the questions that the smart farming try to answer in an efficient way. In particular, our project is mainly related to nitrogen and to nitrous oxide, because this is really important, because you can put nitrogen from with fertilizer on the field that can help the health or the production of your field, but only 30 or 50% of nitrogen is really absorbed. And this leads to emissions of greenhouse gases, as already stated in the previous slide, but also groundwater pollution and so far and so on. The very interesting thing is that the capability of the soil and of the plant to absorb nitrogen is strongly related to a number of factors that start from meteorological and the soil physics condition, for example, temperature, rain that affects, for example, soil moisture and so on, and also obviously on the nitrogen on the soil, on the level that you still have on the soil. This means that probably working on nitrogen will help also to work and to, let me say, lowering the effect of the extreme rain, water scarcity, and so on. And this is what I think it's really important. So as a second effect, we can have also a more robust field. So the main issue and the main point in a smart farming approach is the information. So information is the key. This is also, okay, I have to admit, this is also due to my background. But okay, if we put information in the center of the project, we can split the problem in three parts. The first part is related to collecting data that in Up4Farm project are related to soil, weather, and chemicals. Developing advanced monitoring systems, and what advanced means probably will be clear in the next phase of the presentation. And these monitoring systems will help to take an informed decision about when, what, and where. So the more in detail, the objective of Up4Farm project at a broad level is to define a decision support system supporting farmers to manage the use of nitrogen fertilizers. And we also state before, as we also stated before, this will help also, the same information can be used also to help using a more efficient approach to irrigation and probably also to harvesting. This is a very quick overview of the decision support system and of the project overall. We have more or less three main phases. An hardware module that is related to the acquisition and the treatment of data. In this hardware model, we will collect information starting from outside the project, so monitoring network, satellite data, and so far and so on. But we also develop with the help or with the contribution, I have to say, of the University of Florence, Munster Technological University, and National Italian Council. We develop our own sensors and we train it on the basis of microbial analysis. This is really important because in principle, we acquire information, we collect information about the weather from outside the project, and we develop our own sensor for the nitrogen or nitrous oxide in the during the project. This was the first part, the first half of the project is mainly devoted to this. All this information has been given as a driver to a software model that is based on artificial intelligence that will help the farmer taking decision. And we will apply in the last part of the project this methodology on the pilot. Unfortunately, up to now, we still don't have results about the application on the pilots because this will be available only at the end of the project, only the last part of the project. So this is more or less the same scheme and the same information that I already gives you. In particular, we collect data from Copernicus and the local monitoring station, but also from other national and the European project, mainly related to weather and soil physics, in particular soil moisture. And we develop electrochemical sensor and laser sensors that are completely different sensor, not in what we consider the output. Okay, there are some differences in the output, but obviously it's a completely different level of cost, for example. And we develop it for, in particular, nitrous oxide inside the project. And everything has been collected and gives to the software model that is based on artificial intelligence engine. I don't have a lot of time to spend about what is artificial intelligence and what are mainly the technique that we will use. Probably we need something like three days speaking about this, but okay. I collect everything in a slide. So what is artificial intelligence, in my opinion? As an engineer, is a way to transform data into information. We are overwhelmed by data, but sometimes we don't. We are not able to extract information from that data. Information on what happened in the past, what is happening now, and possibly an estimation on what will happen in the near future. What are the meaning of our data? Is the information that we can extract from that data. And artificial intelligence can help us extracting this information. But it is also a way to transform information into action. Okay, this is much more related to generative artificial intelligence and something like that. Probably every one of you try to ask some question on how to do something to, for example, ChatGPT and so far. So in agriculture, there are a lot of possible applications of artificial intelligence, mainly related to all the field that have been stressed, I think, by the previous presentation and by the question that has been performed to Professor Reines. For example, this is diagnosis and so far and so on. In particular, we focused for a matter of budget and time on the predictive capability of artificial intelligence technique, and also the ability to allow you to extract some information that can lead to indirect measuring something, starting from measured data. So let me explain this point in the last part of the presentation. These are some sketch or example of possible application that we will develop in the frame of the project. So we already have the application. We need the data to train the model that we will collect starting from I think April 25, like that. The project will use artificial intelligence in particular for forecasting, and okay, for forecast, for example, temperature, rainfall, soil moisture, starting from internal and external monitoring data, but also near surface nitrous oxide, starting from the local, the internal, let me say, up for farm monitoring part. And what this means? This means that we will be able to give the farmer something like this kind of example. So the blue line in this context are the measured data, and the red line are the forecasted data. And then we have two let me say, pin that gives you information about the situation of the measured of that sensor. So if we are in a situation of normal dynamic, if we are in a situation of warning, or if we are in a situation of danger because, for example, the soil moisture is too high or too slow, and so far and so on. And in the right part of the panel, we have also some information about how you can trust, obviously, this kind of artificial intelligence model. So are these estimation good? Are not so good? And this is something that we will be able to treat during and online during the evolution of the model. The second application is mainly related to the possibility to use artificial intelligence to perform and to develop a virtual sensor for something. A virtual sensor is something like an indirect measure, we can call it in this way, that start from all the data measured on the field, for example, temperature, soil moisture, rainfall, nitrous oxide close to the surface, but not in the soil, and will give you the data, for example, on the nitrogen in the soil. So it's something that is quite is okay. We are not able inside the project to perform this measurement without we can measure nitrogen in the soil by taking the sample and giving to the lab or some kit, but not in a autonomous way. And and so we try to use this collected data from the University of Florence to train an artificial intelligence model that is able to reproduce at a certain level of detail this data. So this is, for example, what can be the output of this part. We are three, let me say, sensors. Sensor one is an artificial intelligence sensor, so it is not something that exists in as a hardware. Sensor 2 and sensor 3 are the measure of this of the other variable that can be measured hardware. And so what happened is that we reconstruct the output of the sensor 1 on the basis of the dynamic of sensor 2 and sensor 3. The last module is probably will let us a future development for another project that is defining the area where and when to fertilize. So on the basis, in this case, on the basis of monitor data and probably on the forecasting, we can decide if in a certain area we will have the need to fertilize or irrigate, if it is better to move on and not taking the decision another day, or if we don't have to do anything. This is more or less a sketch of the output that the system will have at the end of the project. Up to now, we are, as I said before, we are halfway of the project. So we have more or less all the sensor trained. We will have to put on the field. We have to start a period where the campaign will be interesting in the farmer, in the sense of farmer, and then we will perform the dashboard and all the artificial intelligence part in the last part of the Up for Farm project. So next year probably. And let me thank you all to spend some time with me today, and to obviously to thank all the person that works on the Up for Farm project. This is our website, and this is the wonderful team of Up for Farm. Many thanks to everyone.
Thank you so much for joining us today and for giving us this fantastic presentation. And we do have a question here already. Somebody's asking, do you have partnership with controlled release fertilizer producers, because this type of fertilizers reduce the nitrogen loss extremely?
Okay. No, not inside the project. Not inside the project. Because the idea is to develop a research project that will help this kind of person. Let me say, this can be one of the stakeholder. This part can be one of the stakeholder of the main stakeholder of the project. But the main idea is to give a decision support system that will mimic what they are doing, and see if this can be efficient enough.
So while other people are typing their questions, so you mentioned that you will use AI for forecasting, and then that you get some information like temperature, rain, and soil moisture. These historical data, do you get it from from the Copernicus? Okay, so everything is from that server.
Okay, from sometimes some of the data from the Copernicus, but we have also, in particular in Germany, one of the two pilot, we have a monitoring station inside the field, directly inside the field, that is working in the last year today. I think it started October 23, in the frame of a national project that involved the GFZ, and we are now working on the data agreement to give this data. So probably we will have also information directly on the field, on one of the field. The idea is that German field is very, very, very instrumented, if you allow me using this word. The Ireland one is as a low level of hardware installed. And then we also want to see if this approach will help in both the cases.
Okay, we have two-in-one question here. It says, is there a relationship between nitrogen and soil moisture, and what is the accuracy rate of the results?
Okay, I'm not a strong expert on the nitrogen cycle because I came from an artificial intelligence part. But okay, in principle, it seems that the capability of the soil to use and of the plant to use nitrogen is related to the soil moisture and to the temperature. So this means that, for example, okay, rainfall obviously is a driver of soil moisture, and so this is why we reconstruct these three weather conditions. For the accuracy of the results, we did a work with the National Council on the virtualization of one of their sensors that are the electrochemical sensors that will be developed in this. We work on that case on organic compounds, and the results was very, very, very good. We hope that for the nitrous oxide, the result would be at that level. We have a correlation of 90, something like 0.92 or something like that, and only a small underestimation of the model with respect to the data. For the weather forecasting, in principle, is quite assessed that for temperature, the accuracy is quite high. For the rainfall, we had some issue and challenges to work on because historically there are a lot in the time series. We have a lot of zero, so no rain, and then and the limited number of rainy day. In the last year, the situation changed. So for a model point of view, it's a good thing because probably the performance will be better. But okay, in principle, that's the point. For the photochemical part, I answer just the last question if I can.
Oh yeah, sure, absolutely.
For the weather conditions. Yes, in particular humidity, and but there are work and the team of the National Council that is working on trying to limit this effect. So to give us the more clean information with respect to this condition. But this is obviously one of the challenges of the of the project.
Okay. I just have this like very like last question because we need to close. So, if you end up like kind of doing like an app that is going to be used in the phone, do you have like any kind of training for farmers envisioned in the frame of the project?
Uh, up up to now in the project, we don't decide to develop a app directly directly for on the phone. Probably we will have some dashboard
Okay.
from the laptop or PC, but obviously the train is really important. I think this is not so high TRL to be ready to market, for example. But I think that if you want to enter strongly in the market with this kind of approach, you have to state and try to convince the farmer that okay, you already did this, but you can do it better. With less effort, time for your family, for example, you can spend time with your family instead on the field, and so on. This is something that I think can be something that we have to try to put on the table if we want to enter the market in general for every smart farming application.
Okay. Okay, that's perfect. Thank you. Thank you very much, Dr. Carnevale,
Thank
and
you.
thank you very
Thank
much,
you.
Dr. Reina, for joining us today. And this is all the time that we have. So I hope I'll see you all in our next webinar next week. I'll be sending all the promotion and the emails to everyone who joined this webinar. And for those who are asking if the presentations can be shared as PDF, uh, the recording is going to be available in YouTube, and also it's up to our presenters also, but you will have available the recording in YouTube anyway. So I hope to see you next week, and thank you very much. Goodbye to
Thank you.
everyone.
Thank you. Thank you to
Thank
organize
you.
everything. Thank you.
Bye bye.
Bye. Bye.
Bye.